Okay, we have the stress strain graph for two different materials here, and we want to compare the stiffness. So stiffness is to do with the stress required to get a certain amount of strain, basically the Young's modulus. And the Young's modulus, we can get it from the gradient of the stress strain graph. So the one here, the blue one, has a steeper gradient, so a larger Young's modulus, so it's stiffer. Another way to think about it is that to get a certain amount of strain, basically extension, the blue graph at the top there required a larger stress, so it was stiffer. If you carry on stretching it, it goes beyond the limit of proportionality where it stops being a straight line, and then it goes beyond the elastic limit, and beyond that point it's going to undergo plastic deformation, which means that it's permanently stretched, or basically it doesn't go back to the original length when the force is removed. If you continue stretching it, it will fracture. So fracture basically means break. Okay, so therefore this stress over here on the left hand side is called the breaking stress. The breaking stress is the force per unit area at which the material breaks. For example, the breaking stress of steel is around 400 megapascals. So if you apply 400 newtons per unit area of the steel, then it will break. Now we've got the stress strain graph for a bunch of different materials, and we want to compare which one is the strongest. Okay, the strength. And that depends on the ultimate tensile stress, also known as the UTS, which is a maximum stress a material can withstand. So we need to look at which one's got the largest stress on the y-axis there. So you can see the red one is the strongest because it's got the largest possible stress it can hold. And then followed by the blue, and then finally the weakest is the green one because that's got the lowest stress. Now here we're assuming that they've all been stretched and they break at the point where the graph ends. For these materials, we want to compare which one's the most brittle. Brittle basically means the material fractures without any significant plastic deformation. So for example, glass, which is actually the first graph, and that's the most brittle. If you can see on the top right corner there, it breaks without it undergoing any kind of bending on the graph there, without any plastic deformation. And then followed by that is going to be this material over here. I believe that's ceramic, where it does bend a bit, so there's probably going to be a bit of plastic deformation, but it's not much. And then the least brittle here is the metal here, which actually stretches a bit, undergoes permanent plastic deformation without breaking. Then the opposite of brittle is ductile, which basically means the degree to which a material cannot sustain plastic deformation before fracturing. We've got two materials here, and you can see one of them undergoes a large plastic deformation. So that's the one that's going to be most ductile. For example, metals. While the red line here is not ductile at all, it just snaps without any kind of plastic deformation. Okay, the graph shows the stress against strain graph for three different materials, A, B, C, up to a point of fracture. Compare the materials. Let's start with which one is the stiffest. So that's the one with the steepest gradient. So the steepest gradient is going to be A there, followed by C actually, which is the green one, and then B, but then that changes after a bit. And the strongest is the one with the highest ultimate tensile stress. So we need to look at which one's got the biggest possible stress, and that's A again. So A is the strongest because it's got the highest ultimate tensile stress, followed by B and then C. Okay, which one's the most brittle? So one that snaps or breaks, fractures without any plastic deformation, and that's B. So B fractures without plastic deformation, so it's the most brittle, followed by A and then C, which is undergoing the most plastic deformation. So that also makes C the most ductile. As you can see, a big plastic deformation section over there.